Let's begin the course. In this pre-module, we shall look at an introduction to the POTS system, the OSI model, encapsulation and decapsulation processes, and IP-based networks. The plain old telephone system, POTS. The POTS system, which is the first communication system developed to carry voice signals from one point to the other, was made up of a pair of overhead and sometimes underground pairs of copper cable from the central office right down to the customer's residence. A central office which housed a patch connect frame manually controlled by a telephone operator, and of course, telephone handsets which had no dial. The major concerns for these systems were degradation of analog voice signals as they traveled along the path of the copper medium, the presence of a manual operator who had the access to eavesdrop calls, and inefficient use of bandwidth as the established circuit was maintained for the entire duration of the call even if no voice was being transmitted. We shall now consider the call flow for a user, party A, attempting to place a call to another user, party B, through the POTS system. The call flow process has been summarized into 7 steps. 1. Party A lifts handset to initiate a call. 2. A signal bulb lights, alerting the operator at the telephone exchange. 3. The operator talks to the calling party and requests for the name of the other party to receive call. 4. Operator patches socket of calling party to socket of remote party to establish call. 5. Conversation between parties begin and the physical circuit is seized and blocked from all incoming calls. 6. Call termination occurs when either of the two parties cuts the call and the light above either socket for the parties goes off. And finally, the operator manually disconnects the patch cords. To prevent the degradation of analog voice signals on the copper pair cable, the POTS system was further developed into a digital system. This system, which digitized the analog voice signals, also enabled users to dial numbers in order to reach a destination. To achieve this, the system utilized a process called pulse code modulation, PCM, and this embedded 3 basic operations: sampling, quantizing, and encoding. The PCM process. The first stage of the process is sampling. Sampling converts the analog voice signals, which has a continuous amplitude and time, into discrete times. It then measures the amplitude at regular intervals of time. The second stage of the process is quantizing. Quantization converts the continuous amplitude of the analog signal into discrete amplitudes and then rounds it off to a number of discrete levels. Then the final stage of the process is encoding. Encoding maps the quantized values to digital words that may be 3 or more bits long. Circuit and packet switching. 2 connection types that are used whenever we send data from one place to the other are circuit switching or packet switching. Circuit switched networks. A typical example of a circuit switched network is the type of path that is formed during conversation between two parties on a POTS network. In this type of network, connection from source to node is predetermined and always maintained for the entire duration of the call. There is also no destination addresses since the nodes know the path to follow. Source or destination tears down the connection when transmission is completed. Circuit switch networks have the following problems. End devices must transmit and receive at the same speed. That is, the data rates of the telephones at either side must be the same. There is also inefficient use of bandwidth, as the line is still reserved even when there is no conversation going on. And the operator cannot patch any new call through so long as the lines are in use. Packet switched networks. In this scenario, we shall consider a VoIP call between two users. VoIP data from source is broken down into packets and then sent one at a time from source, router 1 in this case, to the destination, router 4. The packets contain a header defining final destination where user is located. As can be seen, there are many possible routes for the packets to traverse through the one link from router 1 to router 4. Routes can be from router 1, 2, 3, and then to 4, or from router 1 to 7, 8, 5, and then to 4. Unlike circuit switch networks, packet switch networks do not route packets through a predetermined path. Packets also travel separately throughout the one link but get reconstructed at the destination. As can be seen, packet switching has the following advantages. Transmission of packets from router 1 to router 4 continues even if network to routers 2 and 3 are down. There is also cost effectiveness, as there is no need to reserve a full path for transmission of packets from source to destination. Let's assume data from a VoIP application is being transmitted through a communication network that follows the OSI model. Launching the VoIP application, connecting it, and establishing a call creates data at the application layer. This data is broken down into data units and sent from source to destination. During the transmission of data packets, each layer of the OSI model adds or removes control information called header as the data packet traverses through the layers. We will now consider how data is encapsulated in the OSI model. At layer 7, the application layer, we have the original VoIP data plus control and management information labeled as L7 header or layer 7 header. Now, the original data plus the header is referred to as a protocol data unit, PDU. The application layer then sends this down to the next layer below it, the presentation layer. The presentation layer receives the original layer 7 PDU and then prepends it with its own header, layer 6 header, labeled as L6 HDR. The original layer 7 PDU and the layer 6 header becomes the layer 6 PDU. The presentation layer also sends this PDU to the session layer, and this process keeps repeating until it arrives at the bottom layer, the physical layer. This process is called encapsulation, that is, a layer taking the information above it and then adding a header to it. Something unique happens at layer 2, the data link layer. Not only do we have a layer header, but also a layer trailer. Apart from the data link layer, no other layer adds a trailer to PDUs. The physical layer does not add a header or a trailer. It adds nothing because this is the layer which sends the VoIP information across the physical network. The decapsulation process. At the receiving end, the computer receives the information on the physical layer, and then the information will be processed up through the OSI model. After information is received at the remote side, the first layer which would be examined is the data link layer, layer 2. The actual information to be examined here is the layer 2 header and trailer, which are both inside the layer 2 PDU. The header and trailer inside the layer 2 PDU contains control information on how the received data should be treated. The data link layers then takes off the header and trailer messages and then passes on the data to the next layer above it, the network layer. At the network layer, the layer 3 header guides on how data should be treated. This header is taken off and then the data is passed on to the next layer above it, then the transport layer. And this process keeps repeating until at the very top, the application layer, where the layer 7 header is taken off and the original VoIP data is interpreted for the user. This reverse process is called decapsulation. That is, a layer taking the information below it and then removing headers. IP-based networks. IP-based networks have provided a single platform for various functions that traditionally had their own platforms. These functions operate more efficiently after their processes have been migrated onto an IP-based model. The POTS system, after evolving into digital systems, can be used to access the internet whilst the call is in process. The development of VoIP is a benefit derived from IP-based networks. It is true, POTS seems to be nearing its life cycle, but the E.164 numbering plan is one unique feature that keeps waking POTS up from its near death. There seems to be no replacement to this, as the E.164 addresses are not directly routable in an IP or VoIP network. To resolve this, the International Telecommunications Union (ITU) developed a plan called E.164 number to URI mapping, ENUM. Why is ENUM important? ENUM implements VoIP interoperability by enabling E.164 numbers to be used as names in VoIP networks. An example is the SIP address for a user located in Poland. Just as the internet uses DNS for linking domain names into IP addresses, ENUM translates SIP addresses into IP addresses, so it can be used in VoIP applications. Thank you very much for your attention and participation, and I look forward to meeting